how much work is done in pulling the rope to the top of the cliff if we have a rope that is 20 meters long and has a mass of 20 kilograms. Okay, so work done on anything, done on a slice of anything, is weight times distance. So before I continue, I'm going to draw a picture, right? I've got a cliff that is 20 meters and a rope hanging off of this cliff, just barely touching the sea. I'm going to pick a random location on this rope and say that that is H, the distance that we have to go from this slice up to the top of the cliff is H meters. And I'm going to take a teeny tiny slice here that has width delta H. Wow, I keep spelling weight wrong. Okay, so the weight of that little tiny slice is the mass of the slice times 9.8, the acceleration due to gravity, times the distance that that slice has to move, which is H. Okay, the mass of that slice is the density of the slice times the length of the slice. Density times length times 9.8 times H. Okay, so the density of the rope is uniform, so I'm just going to take the entire mass and divide by the length, 20 meters. So 20 kilograms over 20 meters is 1 kilogram per meter. The length of the slice is delta H meters. And then times 9.8 meters per second squared times H meters. So that is the work done on a single slice. So I just need to do the work on all the slices. And that is just the sum where each slice has this amount of work done on it. And if I simplify this, I get 9.8 H delta H. And I'm taking n slices. And then the exact amount of work is what you get when you take the limit as the number of slices goes to infinity. The limit of that sum is an integral, 9.8 h dh, and my bounds of integration are going to be the smallest h can be, the smallest that any piece of the this rope needs to move is 0 meters. This spot right here doesn't need to move at all. And then this spot down here needs to move 45 meters. I'm sorry, not 45, 20 meters. So I'm going to integrate from 0 to 20. When you put this into a calculator, you get 1,960 joules, or do it by hand. It's a very straightforward integral. Okay, part B, we have a surfer that has a mass of 85 kilograms. He is hanging onto the bottom of that rope, and we want to figure out how much work it requires to move him specifically. We already know how much it will take to move the rope he's clinging to the bottom of, but I just want to know how much work it will take to move him specifically. And we're going to assume that he is compact enough that we're not going to slice him up. We're just going to figure out how much work it takes to move 85 kilograms, 20 meters. So work is weight times distance. And the weight of this surfer is 85 kilograms. That's his mass, times 9.8 meters per second squared. So that's his weight, which is called newtons. Kilograms times meters per second squared is called newtons. And then we have to move him 20 meters. And that comes out to 16,660 joules. And then we have to add that to the work you do to pull up the rope. Okay, so final total is 1960 joules plus 16,600 joules, which is 18,620 joules. Okay, now we've got a circular swimming pool. Has a diameter of 8 meters. The sides of the pool are 4 meters high. So let's just draw a picture of this swimming pool. It is 4 meters tall, and its radius is 4 meters. Diameter is 8, so the radius is 4 meters. And the radius is constant. It's the same at the bottom as the top. So this is a little bit simpler than the cone problem from the demo. If the pool is initially full of water, how much work is done in pumping the water out over the side? All right, so I need to find a random slice of water. So let's draw a slice in here. And it's got a little bit of thickness. And I'm going to define my variable as how far this water needs to go to pump out over the top. So this distance, we're going to call H, the distance that the water needs to travel. That slab of water has to go H meters to get out of this tank, out of this pool. Okay, so the work done on my slice is weight times distance. All right, the weight of my slice, well, I know that it weighs 9,800 newtons per cubic meter. So then I just need to figure out how many cubic meters it is. That's its volume. So 9,800 newtons per cubic meter times how many cubic meters it is, and then times the distance it needs to go to leave the pool, which we said is going to be H. Okay, so what goes in these parentheses is the volume of the slice. How many cubic meters is its volume. So its volume is pi r squared delta H. The radius is constant, it's 4. And the slight thickness of the cylinder, delta H, is the height. Okay, so that's the work done on a single slice. The work done on all my slices is just a sum where I add these all up. I have 9,800 times 16 pi H delta H. And I'm going to add these up from 1 to n. And then my work exact is an integral. It's the limit as n goes to infinity, which becomes the integral of 9,800 times 16 is 156,800 pi h dh. And then I have to think about the bounds of integration. So h is my variable that's changing. It's representing the distance that the water needs to move. So because this pool is full, the slice at the very, very top doesn't need to move at all. And the slice at the very, very bottom has to move all 4 meters to get pumped out. So I am going to integrate from 0 to 4. This is pretty straightforward to do by hand, or you can put into a calculator. and you get 3,940,813.8 joules. Okay, for part B, if the pool is initially only half full of water, how much work is done in pumping the water out over the side? Everything is the same except the bounds of integration. So if the pool is only half full, then the smallest distance that any slice has to travel, this would be my slice at the very top of where the water level is, and it would have to move 2 meters because it's half full. So it still has to move 2 meters to get pumped out, and the slice at the very bottom has to move 4 meters all the way out of the pool. So my work here is the same setup as the previous problem, 156, 800 pi HDH, but the bounds are from 2 to 4. The slice of water that's closest to the top of the pool has to move 2 meters, and then the one at furthest has to move 4 meters. So this comes out to approximately 2,955,610.4 joules.